Well, first off, glad to have everyone back listening to me and Demetrios chop it up. Just so you guys know, this is something that we're really interested in because at a high level, me and Demetrios are starting to think about not just what's going on in our immediate circle, but what's going on within the industry at large, and we're thinking about how are people defining MLOps? How are they thinking about MLOps?
Such a good point.
And yeah, a lot of people are trying to set precedent, especially companies like Google, and we're very interested in that. And so today is a continuation off of not just like one subject, but a group of subjects that have come up in this paper. And yeah, we're just having some fun kind of going through some of these main components, and I wouldn't say critiquing it, just kind of breaking it apart. But
Yeah, I before a little derail your train of thought real
oh
fast.
good.
We did mention it seems like Google is really trying to push the agenda here on MLOps. They want to be out in the front and saying what MLOps means and what it doesn't mean. So I find that really fascinating. I guess at the end of the day, it's so that they can sell more cloud resources and they'll be considered the best uh, tool or the best option when you're looking at MLOps tooling. But there may be some other reasons. And one day we'll get somebody. Actually, next week in the meetup, we've got somebody from Google coming on. So
Nice.
maybe I'll have to ask him. I don't know if he knows about
Yeah.
their broader marketing strategy or not.
Yeah. I'm not sure. It'd be really interesting to think. Oh, one thing I do know is that, you know, uh, Google is so large that they can afford to put time into this. They can afford to put
Hmm.
resources into setting precedent for this. And I think that, yeah, like while other companies are kind of just putting this into practice, they're still at the stage where they're trying to deploy their models, they're trying to create business value off of it, and they're not really in a place to slow down and think and say how can other people use this, and what, like, can we set precedent for the rest of the
Totally.
world, right? And not many companies are in a position to do that. And most companies they're just trying to keep their head above water in some ways,
Yeah.
and even thriving in that area, obviously doing good things. But yeah, I think they I mean, first off, like, this is just my own. I've learned so much from Google. Like, I feel like we talk about them a lot, and I wonder why that is. Why do they have such popular papers that a lot of practitioners in the industry will reference, and in a lot of ways kind of think of as like the standard. Um,
Yeah, they're thought
and I,
leaders.
yeah, exactly. And so I think that that's something, you got to give credit for that. They do put out a lot of good stuff. And even this paper, right, or whatever, this article, it just has some good, fun stuff to talk about. And I would love to see this from more companies, to be honest. I want to hear other people's perspectives on how they view some of these things. And I'm sure there's even room for disagreement.
Mm.
And I think I would love to kind of get to that place where we can critically evaluate some of these things instead of just being like, oh, it's the latest and greatest, let's all just do it and follow it blindly type of thing.
Yeah.
But yeah,
Yeah,
hopefully.
that's a little bit of what we're doing here, right? It's
Yeah.
that idea. So what did we talk
Recap.
about last time?
Yeah,
Yeah, let's
let's just
recap.
recap. Yeah. So first up, the kind of flow of things is they start off by breaking down DevOps and its relationship to MLOps, and we kind of took a detour in kind of thinking about one of their presuppositions, or their, like, I guess the assumptions that they're bringing into this paper is basically the value of automating everything and the need to automate everything. And so we also briefly covered another point of view from someone that we've had on the show before, Charles Martin, and thinking about automating just to automate, or is this something that we I guess it's not really relevant to everyone's use case. And we started kind of
Hmm.
thinking about some of the trade-offs there. And one thing that we highlighted was that Google really, if from at least my point of view, this is what I'm noticing, is that what they really care about is maximizing the velocity at which their software actually gets delivered. And they want to do it in such a way that it is really maintainable, really extensible, really testable, really scalable. That's kind of what they care about. And so that's going to obviously shape the way that they think about MLOps, very much from this sort of DevOps perspective. And so honestly, the bulk of the episode was us really kind of walking through their own definition and kind of thinking about some of the major components of that. Just to recap, everyone who wasn't here for the last one, the paper defines MLOps as an ML engineering culture and a practice that aims at unifying machine learning system development and machine learning system operations. That's a pretty good definition in my mind, because it has the cultural aspect, right? There's like these DevOps practices. These are not necessarily like things. And then the actual implementation practices, or like, I guess, best practices for that. And yeah, we kind of broke down some of that, and where we wanted to, we also even talked about continuous integration, continuous delivery, and where we left off was continuous training.
CT.
And, CT,
we can finally get to it. I was trying to jump to it the whole last session, and now we're here. The wait was worth it.
Yeah. And I think what we should do is to kind of continue on this conversation is go back to even what's in the title. The title of this paper is Continuous Delivery and Automation Pipelines in Machine Learning. So a big part of this is continuous delivery. So let's kind of take a step back and think about that. So, we talked about continuous delivery as about being the ability to release at any time, right? And to increase the speed at which you do that. And you're doing that to reduce risks, costs, time. And what they're thinking of is not deploying some single package or single binary, but an entire system, right? Something that you should be able to deploy altogether. And what they defined as continuous training in relation to this is being able to automatically retrain and serve those models. So if something happens, be able to automatically retrain, redeploy in a continuous delivery way.
Now,
you're continuously able to do that.
Is this with just the click of a button, or is this where it does it without any human in the loop?
Yeah, it's a good question. They think about both use cases. So that's kind of the one of the things you need to think about is what events trigger retraining, when to retrain. It's a bit tricky. There's not a one size fits all answer. We're going to talk about some suggestions that I kind of gathered from reading. Mm-hmm. But I guess one of the first things to think about is when. Yeah, I guess this question exactly is, when should we do this? When does this come up? When do you need to actually retrain? And there's two use cases that they bring up is outlier detection and drift detection. So we've talked about drift a lot in a lot of these episodes, but let's start with outlier detection. Outlier detection. Are you familiar with, I guess, the concept of an outlier in a data set?
No, give it to me. I would love for you to break down how it's different than an anomaly also, like the outlier and the anomaly.
I actually think I would think about those as the exact same thing. So if you understand the role of an anomaly as like you have, I don't know, you have a list of heights, right? In, let's say, meters. An anomaly is everyone has like this. Yeah, exactly. Or even taller than that, like, 20 meter, which is obviously ridiculous. But yeah, an anomaly or an outlier is a data point that typically deviates. I think there's I think it's like 2 times or 1.5 times the interquartile range, if I remember my statistics correctly. But there's actually a more kind of robust way to measure that. If it's further than your mean and some of your parameters of your distribution, and it's just like way different, than you would consider that an outlier. And so that's what they're thinking about here is, let's say you're serving your predictions, and for some reason there's some outliers in those predictions. Like, I don't know, if you're predicting a probability that should be between 0 and 1. And let's say, for example, that you're seeing outputs that have 1.5 or like negative point, something. That's something off there, right? There's something going on there, and that's kind of like what you're looking for in in this sort of pipeline. Does that make sense with respect to what it is, an outlier?
Yep, totally.
So how do you deal with this, right? And this is kind of what the bulk of the paper, in my mind, is kind of getting at, is dealing with these things in an automated way. If these sorts of outliers show up in your prediction service, how do you address it? And I think that's kind of what I wanted to start getting into a little bit more today. But before I begin, I don't know, is there anything else that we should think about before I start diving into details? I know you had some questions or comments, but yeah.
One thing that I always love talking about, and I think is very interesting that we mentioned before, but it's worth reiterating on. You have to know that you're having these anomalies or these outliers happening, and you have to know that drift is happening. So that's something the paper didn't even talk about, but you have to be monitoring before you can even do this automated retriggering, right?
Yeah, absolutely. You have to be able to detect these things. And yeah, let's start kind of getting into that then, because I think we'll
Perfect.
hopefully answer some of those questions. So, all right, go. Let's start with drift. That's the most common, I guess, concept that keeps on coming up with all these things. But typically, when you have some sort of deployment, individual, if you have if depending on use case, your individual features may start to drift. Now, this could be a bug, right? This could be something bad, like we kind of brought up, like there's something wrong there. Maybe there's a bug in the code or the data, or it could be perfectly normal behavior. This could be just an indication that the world is changing, right? And that's something that we in our business domain may expect. And some examples of these sorts of features starting to drift could be something like this, right? You know, there's shifts. This happens all the time in the market, right? People's preferences change, right? What's hot today may not be hot a month from now, right?
Yeah,
You
or a
remember those,
pandemic happens.
or a pandemic happened, and then people's priorities are shifted. That's going to affect your machine learning system if you haven't, you know, incorporated that into the data or hasn't learned that behavior. You know, think about just, you know, marketing campaigns, right? You're always shifting. You know, I guess your strategy dependent upon how your customers are actually behaving. So there's going to be, you know, obviously just a normal change in behavior. What about competitors, right? You know, like you have to think about, you know, AWS and GCP, right? I'm sure that they adapt to one another in some ways. As one sets precedent in one area, maybe they feel the need to catch up. Or again, this real life scenario where things just evolve and change. Of course, the weather, right? The weather is notoriously difficult to predict,
Hmm.
notoriously difficult to have like a full understanding of, right? And that's something as we've been studying for a while, but it changes. Weather changes, right? You got the news cycle. So you could think about just like Twitter, right? If I were to you know, build a web scraper to grab a bunch of, you know, tweets from Twitter right now, and if I was to, let's say, calculate the sentiment score on all that, on all those tweets, like on average or something like that, that would probably look different a month from now, or it would have looked different maybe a few months from now when the pandemic started, right? So again, this is all examples of your actual data changing, right? It's evolving, and it may not be a problem. Again, this may just be part of your real life world that you're modeling. Does that make sense so far?
Totally.
And a couple more I think are worth mentioning is, right, is, you know, if you have like you're in Uber, where your customers or where your users are is going to also change. So location, right? That's going to, you know, they're moving from one location to another. Maybe at certain points they're more in this area and other points are there. That's going to affect your model. You have obviously time. Time is a very interesting one too, right? Time is also obviously changing. But if time is a particularly important element in your data set, the most common example I could think of is in like time series data with financial institutions, right? You have you know, prices or yeah, you have prices of these oh my gosh, not only stocks but securities, these
Hmm.
sort of assets evolving over time, you know, being affected by the news, being affected by the weather. So again, these are typically systems that are real, like that we use all the time. And then of course the clients, people are going to be using all sorts of clients, their web browser, their cell phone, their iPad.
Their
That may actually
Neuralink.
yeah, they're neural. That's such an interesting one too, man, by the way. But yeah, you could think about how the actual device that the user is using could actually affect your system and cause change in some way.
Perfect. So mm, let's keep going on this whole idea. Like concept drift is something that I think everyone has dealt with. It's that day two operation, right? Something you definitely need to know if it's happening. We
Yeah.
looked at how it can happen, but let's go a bit deeper into it.
Yeah, good. So again, if the world that you're working in is changing over time, then model deployment should be treated as a continuous process. And that's, I think, like the assumption that Google is making in this paper. Like, why would you want to automatically, or like, why would you want to continuously deliver and have some automated pipeline? I mean, it would make sense if that process needs to be continuous, right? So they're thinking about it like that. And what this tells me, and something that I've been thinking more and more about, is that you need to probably keep your data scientists and your engineers working on that model once that model is deployed, rather than immediately moving on to some other project. Like you mentioned, it's not just about being in a position to detect these things, but being in a position to respond to these things. We talked about earlier about different events. Well, if you have people that are still monitoring that, doing some data science on the monitoring stage, then they're in probably one of the best positions to actually, do something in real time or make those changes to adapt. Versus if you kind of just have this mentality of, all right, it's deployed, it's done, then you really miss out on the importance of monitoring, right? You really miss out on the importance of really learning from what's happening in the real world. And I think we had some chats about this in the community before, but the test environment is a learning environment. You're going to learn a lot of new things about your model, about how your users are, and that needs to be given its, I guess, due diligence, or you need to put some thought into that,
Shout out to Patty in the background.
Shout out to Patty. Shout out to my wife. So, all right, let's do this deeper dive into concept drift. So, all right, I've been kind of getting at this definition in a lot of ways, but I think the simplest definition is whenever your feature or your target distributions change. So features are the actual inputs to the model, and targets is in a supervised learning problem. It's the vector, usually a vector, that's going to supervise the learning process, right? Helping you map inputs to outputs. And so whenever those feature target distributions change, they're thinking about that as concept drift. Does that make sense?
Yeah.
Cool. I read some good papers. We're going to link them here. And I'm going to quote one from this one publication. It says here, data analysis applications, right, where data evolves over time, must be analyzed in near real time. Patterns and relations in such data often evolve over time. Thus, models built for analyzing such data quickly becomes obsolete over time. So in machine learning and data mining, this phenomena is referred to as concept drift. So again, think about this definition where any patterns or relationships in that data are changing over time. Now let's stop there for a second. Think about the real world. That patterns change all the time, right? That's just the way that the real world works. I'm thinking of even the difficulty in predicting the way that these sort of patterns change, right? There's a really good book by, I think his name is Nassim Taleb, but he's this author, really controversial author that wrote Black Swan. And he defines a black swan as like an event that you couldn't have predicted, but has huge impact on the world, like COVID or 9/11 or things of that nature. And what I bring that up because to say, yeah, like real life is just changing and it's very hard to predict, if not impossible. I don't know how, again, I after doing, the research in this area for, and thinking about it, I think that, yeah, we're pretty much always gambling whenever we're predicting the future in some way. There's always a lot of uncertainty and randomness in there.
Completely agree.
We're going to link this paper. It's a really good paper. It's called An Overview of Concept Drift Applications. And we're going to, put that in there because, yeah, it has just a lot of great stuff in there. All right, we're going to keep going. In that paper, they bring up two types of concept drift, that concept drifts that occur. There's sudden, right? Something like a black swan event, something that's really drastically changing your data. You can think of COVID as one, right? No one is really it just really drastically changed things, or something that's gradual, right? There's lots of real life events that they're changing, but little by little over time. So far, so good. Does that make sense?
Yeah. And I think there's also been a great talk by Lena at one of the meetups, and she went in depth on all the different ways that you can get bugs in your model, and you can monitor for these bugs, and how you can also monitor for concept drift if it's happening. So later on, I would almost love to talk about the different tools for this, but I don't know if it's in the scope of this chat right now.
I don't think for today, but we definitely could do that. We could definitely try to, start thinking about what are some good solutions to this. But I guess, yeah, this is all pretty new for a lot of people. I mean, not myself, like I thought about continuous training or concept drift for a little while now, but I think it's good to slow down and actually break it down and talk about it in relation to some of these other concepts. So yeah, we're definitely going to get to that. Good suggestion.
Nice.
All right, cool. So getting back to this paper, I think Google is in a lot of ways trying to address this concern of concept drift, both outlier detection, both concept drift detection. And what they're thinking is that if the world is changing, then you want your machine learning system to change as well. And you're doing that so you could avoid decreased performance. And you're doing that also because you know that it's actually going to get better over time if you're updating it, right? And it's going to adapt to its environment. This sort of robustness is actually necessary for a lot of domains where you need to constantly update your user preferences. Your models are constantly changing because people's preferences are changing. You could think of Netflix with all of their personalization models. Pretty much everyone has, I think, if not their own model that makes personalized predictions based off your user activity. And based off your previous watches, and also some other ways that they do it. But when you have this sort of problem where your world is changing, continuous delivery is particularly helpful. And automation of pipelines is really helpful, right? Because in a pipeline, you have not just the training part, but you have the data components where you're doing that extraction, you're doing that processing, and you're doing all of that in a way that's consistent between what's happening at prediction time and what's happening at training time. And also keep in mind that what they're really trying to do, especially from a DevOps perspective, is you want to minimize the commit to deploy interval, right? That time where I, as a developer, make a commit, push it, and then now it's deployed into the real world through some CI/CD pipeline. But I also want to maximize my velocity software delivery, right? I want to make sure that I'm getting my stuff out as quick as possible to respond to this changing world as quickly as possible. And I guess what they look at in the paper is if you have this whole pipeline as something that's automated, then it's always ready to go. You can now just run that pipeline, and you could do this continuously. So after that pipeline is deployed to some production environment or your target environment, it's going to be executed automatically and repetitively to produce a trained model that is then stored in, let's say, a central model repository. And I saw that there's actually some cool products around this area. I know I forget the name of the one by Netflix, but basically it allows you to see your model's life cycle. You can see the different transformations that were applied to that. It also monitors its predictions over time to detect things like drift.
It's not Metaflow, is it?
Oh, actually, yeah, I think it is. I think it is Metaflow. But the reason why I bring that up is because, yeah, they're thinking about some of these things, being able to, reproduce what got you to this point. And that's what's also really important in all of this is that you're keeping a close tie between your dev or experimental pipeline and then this continuous production pipeline. And what that does is that helps you avoid any inconsistencies between model artifacts that are produced by all of this training and lost my train of thought. Model artifacts that are produced by this training and by the pipeline and the models that are being served. It's very hard to debug these things in a real life system and keep them in tandem. It's just very tricky. Does that make sense?
Yeah, for sure.
So, all right, you got this pipeline. You should be able to run it. Now you're going to either run it on a schedule or based off some events. So certain events, you can have it configured based on your business domain to be triggered when something happens. Let's say you monitor the distribution of your predictions, and whenever there's a change in that or some sort of drastic change, you can write an automatic alert to let you know that that's happening, and then maybe trigger that retraining job. That makes sense. So you could do it in that way.
Mm-hmm.
You could do it based off just like kind of a schedule, like every if you know that there's certain seasonal trends, right? You could say, okay, at this new season, we're going to retrain our model. So it has the latest sort of, world kept in mind. And again, what's cool about this is that if you're keeping the link between the model artifact and the pipeline really close, then they're never severed. And you could answer these really important questions like what pipeline trained them? What data was extracted? What data was validated? How was it prepared? And what was the training configuration and how was it evaluated? Again, and if you have metrics at the stage, then you have nice lineage tracking. You have the ability to really learn from this process. Does that make sense?
Well, yeah, and I think this is huge when it comes to this reproducibility question. that a lot of people are grappling with, and especially those who are in some kind of regulated space, right? This, like,
Yeah.
it's not a nice to have, it's a must have.
Yeah. Yeah, I can oh man, I think that's actually becoming even more important now as a lot of heat comes on some of these big companies. You know, I don't know if
Hmm.
you've been hearing about what's going on with Facebook. But yeah, you know, some of these challenges probably make reproducibility even more important than it already is. It's
Yeah.
already huge just for, you know, the sanity of your development. But now even more for just thinking about it ethically, right? Or for the responsibility that you have.
Yeah, totally. It goes from being something that is a software engineer's reason for it to a much bigger question.
Yeah, yeah. So hopefully this is kind of brought back like, okay, you should have a system in place that can continuously deliver this whole pipeline and respond either through a scheduled sort of thing or based off events, triggered based off events and running based off these in response to some of these events. And if you have continuous training in place, then you have hopefully a close link between what produced that model and the actual model being served in production. And it makes it a little bit easier to debug, to track, to, you know, learn from over time, and also to reproduce. So if you have like lots of different models, right? Like let's say that your system is not just one single model, but lots of different models powering lots of different products and features, which let's say is Google's situation. Google has machine learning embedded into a lot of their products and their solutions. And if you have that going on, where you have tons of different models in production, this can become even more important. You need to have this observability. You need to have this ability to really answer some of these tough questions. Are outliers happening? Is there concept drift? How do we address it? Is this automatically configured in such a way that we could go backwards and change something? And yeah, you know, so again, this becomes really important when you have a very complex system. Like the more complexity you have, the more important it is to kind of automate some of these things. And what we talked about last time was that not everyone's system is like that, right? Not everyone has the need to continuously retrain. And in fact, if you're retraining all the time, that may be a problem, not just with, you know, your data changing. It may just be you're doing something wrong, right? I think part of what machine learning models try to do is to generalize to new instances. It needs to work on unseen data. And if your model consistently sucks at predicting new data, then maybe you're just overfitting. Maybe there's something going on with the actual learning process rather than you know, your pipeline or the sort of engineering perspective of the infrastructure. Does that make sense? Like, you know, it's not
Yeah.
always that. Yeah, go ahead.
Well, I just remember talking one time to a guy who was in the, I think it was the healthcare space, or he was creating, I think it was the models he was doing, it was something to do with healthcare. And he was saying that he can't actually, just by way of design and how it's set up, he can't retrain the models. They put them out once and they're out.
Yeah, yeah.
I
That's really,
think,
yeah. There's a,
yeah, I
yeah.
think what he, if I remember correctly, it was like they were out. It's they put them out, and then they can only retrain after 18 months or something.
What's important to know is that may be perfectly normal, right? That may be part of the business domain, and that's again that like, you know, I know I even in my own company, you know, retraining all the time just isn't important. And
Mm.
it's so it's again, this may not apply to everyone, and you may not need to, again, because there's overhead in automating stuff. There's just, you have to add more complexity to your system to enable this to happen, right? And so if it's really important, right, you need to respond quickly and deliver quickly. This makes sense. And if your world is changing, right, that's when this makes sense. But if you don't really have that sort of problem, then I'm not sure how helpful this is. I'm sure maybe it's nice to think about the reproducibility aspect of it, but I'm just not sure how helpful this would be for some of these companies to aspire to some of this. And this is kind of going back to our, you know, this kind of meta thought of like setting precedent for what MLOps is. I would love to hear from other people in this space to think through, okay, does this have to be part of like MLOps best practices, continuous
Totally.
retraining? You know, is that, or I don't know. Again, in my mind, it makes sense when you have that sort of changing sort of, you know, world. But if you don't, I think it may just be more complex than you know, than it's necessary. Well, We've been kind of getting at some of this stuff with like concept drift, how this happens, when, but what do we do about it? Right? I think that's like one of the biggest questions, right? What do we do about concept drift? How do we deal with it in a production system, right? And I got this cool article that I was reading through from Machine Learning Mastery. Shout out to Machine Learning Mastery.
Great
Stuff.
great stuff there.
They had this cool article a while ago called Gentle Introduction of Concept Drift in Machine Learning. And they have some really good, he has really simple stuff, which I really like, but we're going to go through some of these things and break them apart. Does that sound good?
I love the idea.
All right. So we got concept drift. This is happening in our real world system, right? You can think about, let's say the situation in Netflix, right? People's preferences change, new shows, what's hot now may not be hot later. What do you do about it? Well, one is you do nothing. That's one option. You actually, if you don't need to retrain, you can have just a static model in production. That is a valid option depending upon your use case, right? One choice is to actually not retrain. But that if that's not an option, then there's obviously, you have to start thinking about, okay, should I periodically refit? So that's one way to address this concept drift. And periodically retraining or refitting your data is, if you think about it, when you train a machine learning model, what you're doing is you're helping it learn some behavior, and it does it automatically versus me just programming it. And that's essentially what an algorithm is doing. It's just extracting these patterns. Again, this is like a rough estimation of how you want to think about it. It's extracting these patterns so you can learn some functions, some set of parameters that when I apply something new to it, I get some output that is, again, solving some particular problem. And if the behavior is changing, then I need to have my model also learn that new behavior. So this could be, all right, new data came out from all these new events of the user interacting with our product. We need to now gather that, retrain on that, and then redeploy it. And so refitting is obviously one solution to the problem of concept drift. Another choice, and it may make sense if you have especially like a neural network or some sort of deep learning architecture, you could periodically update your model. So how do you do that? Well, you use the existing model weights as your starting point. So you could think about like using a pre-trained model like BERT or what are some of the other ones? I use these all the time. But yeah, like some pre-trained model, some transformer. You start off with the weights, and then what you do is you basically retrain your model, right? You relearn, you train on from that starting point so that you get somewhat of that benefit of like starting from something that's like you want to use what you already know in some way. And I guess one way to think about it statistically is like having a prior, having a data-driven prior that regularizes the updates that are made to that data. So this is more for your Bayesians out there. But yeah, this is also one way to address that. And for if you're not Demetrios, I don't know how familiar you are with the debate
I've seen
between
it thrown around.
yeah, frequentism and Bayesians. I'm a Bayesian. It just makes sense to me. But yeah, shout out to all you frequentists. But yeah, I like to think about this as like, a prior on your data, right? So where, let's say the last season is a starting point for maybe the next season, but this may not make sense. Maybe you have to actually start from scratch because that's just, it's that different. So again, this may not apply, it may apply, but it's a choice. Periodically update. Another cool option is you can weight your data. So what does that mean? You can weight your data by adding some constant, like, I don't know, some random number, 0.1 or something like that. And you multiply that by some example, like a row of data, in such a way where it's, let's say, the weight is inversely proportional to the age of that data. So you're paying more attention to newer things. And that's one that may actually be relevant for, I don't know, I'm trying to think financial sort of use cases where you want to really pay more attention to what has happened today to inform predictions.
And is that what they mean when I hear freshness of data being thrown around?
Yeah, I don't know about the weighting, but yes, freshness means that it's like the most recent data. Yeah.
Okay.
And I guess one way to address that concept drift is to weight newer data and older data so that your model learns, how to prioritize some of those things.
Yeah, so it gives priority to the newer stuff.
Yeah, and pays more attention to that. Yeah, that's one. And you could do this actually with a lot of situations, like if you have an imbalance problem. So what I mean by imbalance is, let's say, I don't know, on a website, most of the people don't click on something, right? So you're going to have a lot of no clicks and maybe very few clicks, and it's going to be very skewed, maybe like 1,000 clicks out of like 1,000,000 no clicks or something like that, right? So how do you deal with that? Well, you could weight those targets or those labels so that your model doesn't, optimize for no clicks, because that's all it knows,
Yeah.
right? And that could be a problem there, where you have, it's like literally only spitting out no clicks. It's like, well, it's imbalanced, but I wanted to learn a balanced representation of my problem. So yeah, that's definitely another way. Okay, cool. Another one, unless so far so good. Slow down a little bit. Yeah, go ahead.
No, I mean, get through these, but let's talk after you finish this about if you can only do one of these, or is there a possibility to do a little bit of everything?
Yeah, I think so. All right, so cool. Okay, one, so you could weight your data. You could also learn the change. Okay, so like adapt to this environment by assembling or ensembling your models and using subsequent models. Okay, so let's say you have sort of this boosting approach is one way to think about it. What you could do is use these subsequent models to learn to correct the predictions of that static model, that old model. So I don't know how familiar you are, Demetrios, with like gradient boosting, but it's a I guess a type of machine learning algorithm. Some examples are XGBoost, AdaBoost, Gradient Boost, Cat Boost, Light GBM. These are very actually really popular algorithms in like the Kaggle world or the data science world. But you could actually configure it and use that to actually help alleviate this problem. Because one of the things that they do is they learn from the residuals of previous models. They're learning how to correct the errors of what was passed in before. And that's one actually technique to deal with, there's a lot of things that it's trying to adjust, but it ends up actually building a very predictive model if you do it this way. And this is, again, just a technique. You could think about actually, instead of just using one set of models, you could use a suite of models, maybe a linear model, a tree-based model, a neural network, and ensemble them in such a way, maybe through like a stacked sort of approach or a voting approach, combine them to actually, kind of learn this change and adapt to it. So that's one technique. Another one is you could basically do a bunch of cross-validation to see which one does the best and choose the model that performs the best. So if your model has a decrease in performance and you have concept drift, retrain your model and choose the one that has the best performance through cross-validation. Now that's like a pretty naive approach because you should probably be doing that anyway. But he stated that here, and I don't want to go too much more into that, but yeah, that's something I guess it's another choice. And another one, this is something I'm familiar with like time series or forecasting, is you could change the data by removing any trends or seasonality. And this is called differencing the data. So what you do is you basically prepare your data through some regular standardization, which is where you subtract by the mean and divide by the standard deviation, your covariance. You could scale it, maybe min-max scaling. And then what you do is you reduce the effects of those input variables in the future. So you could change differencing. It's just a technique to deal with seasonality and trends. And this is typically happening in like time series modeling, where certain assumptions are actually required for you to be able to use some of these models, like stationarity. Stationarity is a particularly important concept with time series, because if your mean and your variance are changing all the time, then you have non-stationary data. You have data that there's trends in it, things are changing. And certain models, especially statistical models, require stationarity to be sort of in place before you can even apply it. And this is typical with lots of machine learning algorithms, like with the linear regression. Certain assumptions are required. I think one, if I remember correctly, I haven't thought about this in a while, but like your residuals are normally distributed. These are assumptions that are required for you to actually, I guess, apply this technique correctly. So yeah, that's one. And the last one is if you're detecting this stuff, you could check for staleness before you deploy, or at least try to measure it. So actually one way to deal with it is to even just be able to actually detect it before you deploy it. So before you deploy, maybe have an automatic test that runs in your CI/CD pipeline that just checks if the distribution has changed drastically from a previous point in the past or something like that.
And when you say staleness, you mean this drift is happening already?
Yeah, or like there's a decrease in performance because of the age of your model. The model is now stale or no longer fresh. Does that make sense?
Yep.
So we got all these cool suggestions, and for listeners out there, I'm sure you guys have other ones. We'd love to hear them. But yeah, these are some ways to address it. Hopefully this gives you at least a starting point to dive deeper into some of these things. Now, going ahead to what you were saying, Demetrios,
Yeah.
go ahead. Can you restate kind of where the direction?
Yeah, I wanted to know, can you get a little combo meal going on, or does it have to be all a la carte?
Yeah, I think so. I think you can. I think you can definitely do a combination of these things. Like one, I think that you should, at least with some sort of regularity, if your world is changing, you could refit your data, retrain your data. So that's one. I think what you could also try out is alongside retraining it, definitely do some cross validation and model detection, or model, choose the right set of models based on cross validation. You could also try, obviously, detecting staleness before. So that's even like the first step, I would say, is like, so you could do that. And then if you do detect it, retrain it. And I think, honestly, even that one point about changing your data, so weighting it, differencing it, those are some things that you could probably do in tandem. Personally, like when it comes to this sorts of stuff, data science is, and I've said this before, it's like arts and crafts. I'm going to try a bunch of different things to see what works. I think I'm empirical when it comes to this sort of stuff. I'm looking at, like, I want to see evidence, I want to see data, I want to see real observations. So it's, in theory, none of these are better than the others. And also, in theory, not all of these apply to every situation. So it's going to be based off, your use case. But I think you could actually combine a number of these. And one that I think that everyone could do is just check for staleness. If you have, let's say, some sort of central model registry where you have each training artifact, right, with its date of when it was created, some metadata around what produced it, and maybe even like the data that produced it and the steps that were taken, then okay, this is a month old. And if you already have discovered the effects of staleness on your pipeline, like if you know that things a week old should be retrained and you have a model that's a month old, you already have a trigger to tell you to now retrain all over again. So I think that's one thing that you could always do, is just figure out, does staleness actually impact your performance? And
here,
that's something,
obviously, that is something where it would be much better if it were automated. You get an alert on that, right? Like that seems like a no-brainer for automation.
Yeah, I think so, to be honest, because these sorts of things maybe can be easy to miss. I think that's actually one of the nice successes of machine learning, is that it catches things that we would normally miss. Like you think about why ML is so successful for like image recognition problems, where you're, let's say, trying to detect a growth in someone's lung, right? So you're looking at all these images. Why are they so good? Why are they better than humans at that? I think it's because there's nuances there, things that are very easy to miss. And I think these sorts of things, monitoring and like outlier detection, drift detection, I think these things can be more subtle than we may realize. And for those types of things, I think that's where technological solutions actually excel, because technology is good at kind of encoding what we already know and doing it in an automated way. So I think, but it may, again, if that's not a problem, then don't put an automatic trigger. That just seems like it's overkill for a process. But yeah, I think so. I think you can do a few of these things. I think you can there's some things that you could do now, even if you don't know if you have a problem, like just checking the effect of staleness. Shout out to the another paper by Google, the ML test score, where that's actually one of the tests. You should check for model freshness, the impact of model staleness on your performance. If you don't know that staleness is a problem, that's something you should figure out.
So let's move on to the question that I asked you, I think a few weeks ago. Like, what did I say? It was something along the lines of break down each step along the way that a data scientist is going through when they're creating and putting their models into production. Yeah,
good. I think it's going to take a little bit longer. We can probably go on a bunch of digressions here. So I think what we're going to do for today, if that's okay with you, man, is we'll briefly start this process, just kind of get the ball rolling. And then when we come back, really start bringing this into perspective with honestly what the paper is really getting at is this, maturity of this sort of process and the level of automation in that. So this is actually really important for everyone listening to kind of follow along with what the paper is assuming or kind of thinking about as this data science process or the machine learning pipeline or workflow. So let's get started on that. This is something that I think is really cool. All right, so typically your data science process is going to start with extracting data from some source or typically multiple sources of data. So it could be an online database. So maybe this is something like Hive, where you have low latency, so you need to be able to quickly read. Maybe you're pulling it from a MySQL database or some sort of SQL database that is relational. So it's actually not something that you need to read from really quick, but rather something that you need to be able to join together things and look at it in different perspectives so that you could have a different view or analyze that data. So certain databases are optimized for analysis. Or you may have a streaming sort of architecture where you have these publisher subscriber model where you can subscribe to some topic and you need to get that data from that topic. But I guess in a nutshell, what you're doing is you need to select and integrate whatever relevant data, whatever data is relevant to your problem from various sources for that specific task. So whatever your task is going to inform the data that you select, even the constraints around that data, the architecture. If speed is a concern in your online environment, or if you have more of an offline environment and speed isn't that important, then you have other choices. So the first step is thinking about which sources you're going to use. So far, so good.
Real
and
good.
Please interject, ask questions, examples, anything along the way, Demetrios.
Cool.
So, all right, you got your data. You need to start analyzing it. So typically this is called exploratory data analysis, so EDA. And this process is where you're trying to understand what's available, and you're using it to kind of do detective work, to really dig deep into the data. And this is where a lot of data scientists excel in, just kind of playing around and trying different things. This is a very messy process. This is typically happening in notebooks. This is manual also. You're not going to, there's ways to do automated EDA. But at this step, you're really trying to understand the data schema. You're trying to understand the characteristics of your data. What's going on here? What are some patterns there? You're identifying maybe at this stage also how the data needs to be prepared, right? So if your data source is images, you need to start thinking about how you're going to transform that for a model. If your data is text, how are you going to process that? If your data is a bunch of continuous numbers, how do you need to scale that? And what you're thinking about is if you're already set on applying machine learning to your problem, because again, this may happen and you're not even doing any machine learning, but you're doing data analysis, you're thinking through how can you leverage your data to solve problems. And just a little note here for anyone that's listening, maybe more of the senior leadership at some of these companies that are less technical. I think it's super important to help people understand that this is the first step. You should, if you haven't applied machine learning to your product or your business, this is what you need to do. You need to really spend a lot of time analyzing your data, learning from your data, and thinking about ways that you could leverage it to solve your problem. And if you can't solve your problem using the data in a manual way, it's going to be a lot more difficult to solve it in an automated fashion. In other words, you're not ready for machine learning. Because what essentially machine learning does is it automates some of that learning process, right? And if you can't leverage it manually using some baseline or some heuristic, then a model, again, if you can't do better than that, then a model, it probably won't be worth it. And again, it requires all that overhead that we all are very familiar with and complexity.
Yeah, and I think there's been some great talks on this. I know you have a lot of experience with this. You've been going through it in your consulting and whatnot. And so the other talks that I found fascinating was the one by Vin Vashista, and we'll link to that also because he really broke down this whole idea in depth and was talking about the need for ML researchers and the need to really structure what the business case is and what you need to try and use ML for, and if ML is really what you would want to use in this use case. And the other one again is, I think we keep quoting Charles Martin. He had a great talk on this. I mean, he's been around for ages and is working with a lot of big names, has worked with them, is continuing to work with them. And so he knows a lot about that whole dilemma.
Yeah, I think we could even at some point in the future dedicate a whole episode to that. Like when is like even framing the problem, and then framing the problem for machine learning. These are preliminary steps before any sort of like machine learning pipeline needs to be built. But yeah, these are yeah we'll definitely keep note of that because that's something I feel like I could go on a tangent for. But yeah, all right, you extract your data. You're analyzing it, you're learning from it. This is where the data scientists and AI scientists will be, the analysts. You're thinking about the data schema, you're thinking about the characteristics. You're also thinking about even now, how would you model it? Like what's available, what's possible with this? Again, very researchy, very open-ended. But now, once you have a sense of what you have and you have an idea of what you need to do to it, then you need to start preparing that. You need to do the data preparation stage. So the data is going to then be prepared for that specific machine learning tasks. And this preparation involves, cleaning the data. Okay, I mean, there's all sorts of data cleaning process, but like as you know, like most of the time a data scientist spends is at this stage, is processing it, preparing it, cleaning it. Here's where you also start thinking about how you're going to split your data. What's your cross-validation strategy? How are you going to know if you're overfitting? How are you going to know if you're underfitting? How are you going to have a proxy for how well your model generalizes in the real world? So at this step, that's where you're doing that. You're splitting it typically into a train, val, and test set. Here's also where you're going to apply your data transformations and your feature engineering to that model to solve that specific task. And what the output of this step is typically a bunch of data split into its respective folds. So your train fold, your validation fold, and your test fold. And just to recap on how this typically works is you're going to use your training fold to train your model. But you could also use that training fold and split it into a train and val fold so that you could use your validation fold for things like early stopping. So the reason why that's really nice is that it's like an automatic way to know once you start overfitting, stop training. And you could use your validation set to do that. You could also use your validation set to then, again, validate your model to see how it's doing. And this is where you typically use the train and your val set for hyperparameter tuning. So running hyperparameter search to see what different parameters do we have a lift when we try this out, when we try that out. And again, a very experimental process still. I would even say I don't know, Google, this is how Google put it, but I would break apart data preparation into feature engineering and data preparation, because feature engineering is its whole ballgame. I mean, literally, there's all sorts of companies that are dedicated to this component of an ML pipeline. We have Tecton, right? We have Feast, we have Clockworks, right? Or
Logical clocks, Scribble data.
Right? Scribble data. There's all sorts of people that are working in this space, and excuse me if there's anyone I missed. All sorts of people working on that specific part because it needs its own, sort of space, I guess. So when you have this stage, some parts of this may be automated, some parts of this may be not. I think if you already have an idea of what you're doing, then maybe you already have an ETL pipeline in place, an extract, transform, load pipeline that's pulling that data, extracting it, processing it, engineering it, and then passing it into a model, maybe in real time for real-time recommendations, maybe offline to do batch predictions and score your data. There's a lot of different things that this could look like. But does that at least give you a sort of sense of this sort of space, data preparation?
Sorry,
Sweet.
I was on mute. Yeah, for sure.
Oh, good. All right. We got a couple more things before we leave off. We got model training. Sorry. So, okay, this is where a lot of time is spent in the machine learning ops space talking about. So, data scientists implements a bunch of different algorithms with that prepared data to train various models. And then maybe that algorithm is subject to hyperparameter tuning to get the best performing model. What the output of this step is a trained artifact. So for those of you who are familiar with these sort of compiled languages, it's like you compiled your code. You have your binary ready to go, your executable that's ready to be run in some sort of serving environment. And at this step, you can already have, once you have this artifact, it could be deterministic, meaning whenever I apply it with the same inputs, I expect to get the same outputs. I mean, typically that's how it should be. I don't know if where you'd have inference that's actually random or stochastic, but yeah, you have at this step a trained model, a model artifact. Now this could be in a model registry, This could be in something like maybe Metaflow is what it was called, right? This could be something then that's sent into, I don't know, like a deployment platform like Algorithmia. This could be something in the AI platform where you have a prediction service. I mean, there's all sorts of, ways that are where stages that this step could exist in, but you have a trained model. Okay. Once you have that trained model, you need to evaluate it, and you're going to do this on some holdout sets. So if you broke your data into a train, val, and test set, the holdout test set is what you're going to be used to actually evaluate your performance. So how well is my model generalizing? And you never show this part of the data to your model during training time. If you have a time element in respect, you need to make sure that you're avoiding data or target leakage or leakage. Meaning you don't want your model to see things in the future. You don't want it to cheat. You don't want it to memorize this stuff. You want it to learn how to actually generalize to solve whatever that problem is. So evaluation is super important because what you're getting at this step is metrics to assess the quality of your model. You could see, is the scores on my test set very different from my val and train set? That means you're overfitting probably. Am I doing really well on the holdout set, but doing, shit on the training set? Again, there's all sorts of things that you could start thinking about, but this is the stage that you would look at the metrics to assess, the quality of your model.
Yeah, for sure.
Now, we got a couple more. Are you with me? Still with me?
Yeah, on this model evaluation, I was just thinking, like, this is where you'll potentially have to go back, right? Like, do not pass go. Or no, I guess it would be where you just like have to start over and say, all right, now this wasn't working as well as we thought. Let's go prepare the data in a different way.
Yep, exactly. That's exactly what you should do. If you tried, like 50 features and not all of them are valuable, go and do feature selection, reduce it down to the most important ones. If some data source turns out to really decrease your performance of your model when you added it, then go back to that stage of feature extraction or whatever. But yeah, this is typically where you're kind of getting a sense of what you're doing. You should slow down. You should do some data science here and do more work at the level of like different levels of granularity to see how it's doing, especially in different slices of the data.
At the risk of derailing this conversation even more, how do you think about that whole process with the tooling that you're using and how you're architecting that? Is that something like, how are you running tests and then going back and saying, okay, well, these features, how do you know that these features are the ones that were taking up too much use? And do you understand the question?
Yeah, absolutely. I think, and maybe I'm not answering it the best of ways, but because this is fresh in my mind, I've been doing a lot of reading on system design and architecture. And I'm thinking that certain design patterns probably make that easier to go back. So for example, in object-oriented programming, there's this acronym SOLID. Are you familiar with that at all?
Nope.
So just a quick overview. I don't want to go on too much of a tangent, but SOLID represents single responsibility, the open-close principle, Liskoff substitution, interface segregation, and dependency inversion. And these principles are like, kind of things that you use to, not things, these are patterns that you use to build architecture or software that is extendable, right? Meaning it's easy to change. It's modular. There's this separation of concerns, and this thing does this one thing and it does it well. It also has this ability where you're building the right abstractions where a class encapsulates data and functionality. There's lots of different ways that this conversation go, but the reason why I bring that up is that if you're building your pipeline using good design patterns that are tested and have been used a lot, it probably is a little bit easier. Like for example, Liskoff substitution is this principle that, and this is typically when you have I don't know how familiar you are with this, but if you have multiple classes and you have a parent class and a child class, the child class should be substitutable with the parent class. And what that means is that if you're extending the behavior of these different objects, it should be somewhat easy to modify them or replace them or substitute them with different components. And if you don't have that, then maybe you have a very tightly coupled system. And when you have a lot of tightly, very tightly coupled, it's very hard to change. It's very hard to improve. And so I think one of the first things that you do is not, besides just thinking about MLOps, is actually good software design patterns, and using that to build software that is actually easier to work on. And if you have this microservices architecture, I was reading this really good article. We'll probably put a link to that as well. But instead of solid, you could use another acronym called ideal. So they call it, right here where there's interface segregation. So if you have, a Python client, a Java client, each one of them has what they need, and they all interact with your platform without having to worry about all the details. You don't have like a one size fits all. You separate different interfaces. That helps with how you interact with this. You have the deployability. How independently deployable is each component of your pipeline? This is huge in a microservice. So like, I should be able to deploy my feature engineering pipeline independent of my serving pipeline. And being able to make changes to them and update them in a through continuous integration, and then continuously deliver them is huge. Also, do you have an event-driven sort of setup, or do you have your architecture set up in such a way that you're responding to certain events, which is kind of this continuous delivery thing. Also, you have a highly available system, and there's ways to do this where like maybe you distribute you have a load balancer, or you're sharding your data across multiple machines. Like, there's all sorts of things. And last but not least, loose coupling and single responsibility. And the reason why I bring up these design patterns is that it makes building a system that is scalable, that is reliable, that is easy to evolve, that I had this note because I was literally thinking about this, that is available, meaning like if there's a lot of uptime, it's not going down, you're able to respond, is efficient, it's using what it needs. So think about like auto scaling and how that plays a role in an MLOps pipeline. And then how serviceable or how manageable is it? Like, how easy is it for me to go into the system and change things, fix things? And so I think that, like, again, good software, and this is why DevOps is actually so relevant for MLOps, is because it's like there's already a lot of this has been thought about and dealt with. It just has to be kind of reconfigured and kind of customized towards your machine learning problem. But yeah, I think, sorry to go back on this tangent, when you're at the step of evaluating your model, and if you want to go back and change certain things, I think actually having a system that is architected with sort of these scalability concerns, like having a good distributed system or whatever it is that you want to think about, having those in mind makes it a lot easier to do that. So that was a long answer to your question.
That's perfect. Yeah, well, it was a bit of a blank in my head, like, well, how does that work?
Nice. Well, maybe we should talk about that, design patterns for MLOps. Maybe that's like a cool,
for another one. Exactly.
All right, so three more things, and then we're gonna round it up. So thank you so much thank you for you guys who are listening. I'm sorry that I talk too much. As you could tell, I'm very passionate about this. And again, if there's anything that you would like to add to this, feedback on what we're saying, please reach out to us. All right, but I'm going to keep going. All right, so you have evaluation, now model validation. All right, the model needs to be confirmed to be adequate for deployment. There's a lot of things you could do. You could check the serving environment. Does it have the memory that it needs? It has the CPU that it needs. If you have a GPU serving environment in your serving environment, can you properly load your trained artifact? You could do things, for example, checking if the predictive performance is better than a certain baseline. So maybe you don't even redeploy that new model unless it meets some standard. So again, this is going back with this sort of continuous delivery. You can automate some of these things to make it a little bit easier to keep getting your model out into production. So there's model validation. Then there's the model serving component, which is where a lot of people are working on. I know, again, I'm sorry to think about not bring up every vendor that I know. I'm just thinking of the ones that are in my mind. But Algorithmia, as a deployment platform, is specifically focused on this part of the problem, right?
Yep.
So there's some people that are Seldon,
Model Zoo.
AI, there's the AI platform in GCP. You have AWS. You have those cloud functions. There's all sorts of services built around just the serving component. And so what you're doing is, once you have your validated model and it's deployed to your target environment, so this could be your staging environment, your dev environment, or your prod environment. Now, what you're going to do is you want to do some of the following. So you're deploying your model as a microservice, as like a REST API. So there's representational state transfer going on. You could also do it through gRPC API if that's something that you're using, which by the way I use. We have both a REST API and a gRPC API. And it's really nice for a lot of reasons. gRPC is pretty cool, but that's a whole nother conversation. You could also have your model be embedded into some edge or some mobile device. So we talked about these Internet of Things, these edge devices, how it's actually embedded in your application and doing real things. So our iPhones right now are doing this facial recognition. It opens up your phone based off how it recognizes your face. That's AI embedded into your application.
Yeah, we talked
You could
pretty
also,
at length with that last night when I was talking with Kai about Kafka.
nice.
So I'll link to that too.
Yeah, nice. Shout out to all these links. And you could also have your model being a part of your batch prediction system. So if you have going back to this, you serialize these predictions, or not serialize, you create these predictions, you materialize them, and then you store them in some database. I remember this being called scoring, model scoring. So you're scoring some data, and then you're putting it someplace else that you can access later on. And this is actually pretty common. Like I know Netflix, a part of their recommendations come from data that is already prepared for. So they make recommendations and then they supplement it with real life event data to personalize it to the user. But in a batch prediction system, you're making predictions offline and usually in bulk. You're doing a lot at a time.
Mm-hmm.
And last but not least, the model monitoring. This is a definitely important stage of the data science workflow because now you're evaluating the predictive performance of your model and potentially learning from that to invoke a new iteration of the process. So if you have this sort of event-driven architecture where you're thinking about certain events and how to drive changes to that or affect changes to that, this is where you're going to be really looking at. And we're going to leave here and get into the next section next time, where what we're going to do now is we're now going to look at the level of automation of all of these steps. And Google is thinking about the level of automation as actually your level of maturity of the machine learning process. So what they're thinking about is how this reflects the velocity of training new models given new data, or training new models given a new implementation. And so what we're going to discuss in the following sections is we're going to describe these 3 levels of MLOps, starting from the most basic level, the most common level, which involves basically little to no automation, up to what they look at as the most mature level, where everything is automated and you have continuous delivery and you have these automated pipelines. So I think that's it for today. Demetrios, you want to leave with any closing notes?
No, this was great, man. You enlightened me to so many new topics and ways of looking at the world.
Well, good. This has been super interesting to learn about, guys, and we're really excited to continue some of this. Shout outs to anyone who's kind of talking to us offline, helping us prepare some cool things. We have some cool things coming up. But yeah, I think that's all for today. I think, guys, just for, thank you for listening. Please provide any feedback to me and Demetrios if you have any questions or comments. And we look forward to talking to you guys soon on the next.
If you're not in our Slack, get in there, talk to us on there. Otherwise, leave a comment down below if you're watching this in the future.
All right, my guys, be well. Peace.